to today's episode lesson. Please, we are going to be looking at nuclear chemistry class with the H2O. Now, this is the second part of radioactivity, and that's why it started as radioactivity part 2. So if you don't say you just come across my YouTube channel and you never watch radioactivity part 1, you can go back to watch my previous video on radioactivity. Now, in today's class, we are going to be looking at half-life and decay constant. Yes, we are going to be looking at half-life and decay constant. Now, if you are a student preparing for JAM exam, or you are writing WAEC exam, or GC, or other related exam, please do well to subscribe to my YouTube channel. And do well to on your notification bell so that whenever we post video, it will get across to you. Now, let's begin with our decay constant. May we start with decay constant. Okay, what is decay constant? Decay constant, carry your book and your pen or your right hand. Decay constant is the instantaneous rate of decay per unit atom of a substance. The instantaneous rate of decay per unit atom of a substance, or the rate of decaying of an atom per second. Yes. Okay, write it down. Now, decay constant gets two important formula that we are going to consider in this class. Now, what's the first formula for decay constant? Take a look at this. Decay constant, don't forget that this symbol is called lambda, which is the same with wavelength in wave. Decay constant is equals to into over half-life. Yes, this is the first formula for decay constant. Now, if you press in your calculator, you are likely to get 0.693 over your half-life. So this is formula number 1 for decay constant. Now, this your half-life is always given in either seconds or minutes or hours or days or weeks or months or years. Take note of that. Yes, your half-life is either in seconds or in minutes or hours, days, week, month or year. So half-life is actually time-based. Okay, now because you have decay constant equals to 0.693 over half-life, it means that the unit for decay constant will either be per seconds. If the half-life is given in minutes, it will become per minute. If it's given in hours, it becomes per hours. If it's given in days, it becomes per days. Per days. If it's given in weeks, it becomes per week, per month, or per year. So it is actually the inverse of your half-life. Okay? So take note of this important formula. We can take this as formula number 1 for waiting for decay constant. That decay constant is 0.693 over half-life. Crammer. Okay? Now, formula number 2, come closer. Decay constant is equals to number of atoms. Number of atoms or number of radioactive atoms or isotope decaying per seconds. Decaying per seconds over total number of atoms originally present, over total number of atoms originally present, or you can say initially present. Originally present. So take note of this important formula. Number of atoms decaying per second, so number of atoms originally present. Now there are cases where we have to equate this guy to this. Yeah, there are questions where you equate formula number 1 to formula number 2. For instance, I can say 0.693 over half-life, watch this carefully, is equals to number of atoms decaying per seconds, number of atoms decaying per seconds over total number of atoms originally present. Total number of atoms originally present. Please note this. Take your book and your pen and note it. So there are cases where we have to equate this formula now with this one. But most importantly, this is your first formula for what? Decay constant. And this is your second formula for decay constant. So we go take this one as what? Equation 1. And we take this guy as waiting, equation 2. And again, don't forget that half-life can be in seconds, minutes, hours, days, week, months, or years. Then your decay constant, which is the inverse of half-life, will be in per seconds, per minute, per hours, per days, per week, per month, or per years. Note it, okay? It is just the inverse of your half-life. Now, because of this formula, I'm going to give you two important questions. One from Neco exam and one from JAM. Now, we are going to use this formula to solve before we continue. Let's do that quickly. Let's take this question. Now, this question is from Neco 2008, question number 10. Look at this question closely. According to this question, he said the half-life of a radioactive isotope is 5095.6 seconds. This is the half-life. Calculate the decay waiting constant. Very easy. Now, if we bring out the parameters out, we have half-life, watch carefully, equals to 5095.6 seconds. Now, what is our decay constant? We don't know. According to formula number 1, the one I gave you earlier on in this lesson, that decay constant is equals to 0.693 all over waiting all over our half-life. You see I'm now, okay, see, what is your half-life? Very easy, just simple substitution. You have decay constant equals to 0.693 divided by the half-life. See the half-life, 5095.6. So let's divide that quickly. Zero 0.693 Is that my calculator? You know they are. Now let's divide this quickly. 0.693 divided by 5095.6. So our decay constant is 0.000135 or 136. Yeah, these are our decay constant. Okay, if we take into standard form, you have 1, 2, 3, 4. So you eventually have decay constant equals to 1.36 times 10. Don't forget we have moved our decimal 4 times, raised to the power of -4. Yes. Now, since your half-life is given to us in seconds, it means that the decay constant is waiting per second. So this is your decay constant. Let's take question number 2. Now let's take this second question. Question number 2 is from JAM exam. That's University Matriculation Examination 2009. Question number 47. Let's take this question. A piece of radioactive material contains 10 raised to the power of 20 atoms. Okay? Now, 10 raised to the power of 20 atoms is the number of atoms that was originally or initially present. The quantity of atoms that was present initially is this one. Okay? So we can say number of atoms initially present, number of atoms initially present, okay, is equals to 10 raised to the power of 20 atoms. Yes. Number of atoms initially present. Okay, so if the half-life of the atom is 20 seconds, half-life half-life is 20 seconds. Let's look at it carefully. 20 seconds. The number of atoms decaying in the first second is what? The number of atoms decaying in the first second simply means number of atoms decaying per second. Remember the second formula I gave you for decay constant. So we can say that number of atoms decaying per second, decaying per second, let's do it this way, is equals to 18 x. We don't know. Okay, so how do we solve this question? Very what? Easy. Look at it carefully. Let's begin by writing the formula for decay constant. Number one, decay constant is 0.693 over your half-life. That's formula number one. Over your half-life. That's one. Number two, decay constant is number of atoms decaying per second, which is what we are looking for, over total number of atoms originally present. Okay, so number of atoms decaying or disintegrating, decaying per second over waiting total number of atoms originally present. Don't forget. Okay, now if we have these two important formula for decay constant, according to this question, they gave us the number of atoms initially present as 10 raised to power 20 atoms, and they gave us the half-life as well, 20 seconds. They now said we should calculate for number of atoms that is decaying per second. Just like I told you, you can combine this formula with this one to solve this question. Let's do that quickly. Now, if this one is 0.693 and this is half-life, and then you have this, we can equate these two together so that we have 0.693 over half-life, hold on, equals to number of atoms decaying per second. Let's use this symbol, number of atoms decaying per second. Let's do it this way, okay? Then over total number of atoms. Let's write it this way, total number of atoms. So if I get this formula now, I feel solve this guy. Why? This is 0.693. Watch carefully. What is our half-life? Our half-life is 20. You see am now? So you put it here. You have 20 equals to, this is what we are looking for. And they said number of atoms decaying per second. Now we are calling it waiting now x. So we can write x here over total number of atoms that was present. They gave us a piece of radioactive material contains 10 raised to power 20 waiting atoms. So you have 10 raised to the power of 20. What do you do? Simply cross multiply. X with times 20, you have 20x equals to, this go times this, you have 0.693 times 10 raised to the power of waiting 20. You see am abi? Then we divide both sides by waiting, the coefficient of x. So we divide here by 20. We divide this guy by waiting 20. So this cancel this. What do we have left? We have x equals to, let's divide 0.693 over 20. 0.693 divided by 20. You have 0.03465. 0.03465 times 10 raised to the power of waiting 20. So very easy, class. Wait till we can't get, watch. I'm going to take my point from here. If I do 1, 2, I have 3 points. You can approximate from here to become 3.5 times 10. Remember, you have moved 2 times. This guy now 20. You remove 20 from here because you have moved 2 times, so that it becomes 18. This is the answer to the question. Or you can simply say, if you move your point 1, 2, you have 3.465. You can say 3.465 without any approximation. Then these 2 zeros, which is 2, you remove it here, times 10 raised to the power of what? 18. This is the number of atoms decaying per second. Let me give you a simple text. Now listen to me, this is a class work for you. Now to prove that you actually understand this video lesson, you have to solve this questions for me. You are going to solve question number 3, okay? If the decay constant of a ready substance is 0.231 per second, the half-life will be what? Solve it for me using the formula I have given you, okay? Question number 4. The radioactive isotope has a decay constant of 10 raised to the power of -5 per second. Calculate the half-life. Use the same formula. Question number 5. The half-life of a radioactive isotope is 6930 years. Calculate the decay constant. Now, if I want to calculate the decay constant, it means that my decay constant will be in per year after calculation. That's why you have per year, per year, per year. Because why? The half-life is in what? Is in years. These other ones will be in what? Seconds, because you have per second. So prove to me that you actually understand this video lesson. Now, if you are unable to solve this, it means that you have to watch the video again and again so that you get it clearly. Okay? Please don't forget to subscribe to this YouTube channel if you are a student preparing for JAMB, because this question cut across questions from JAMB, WAEC and Neco, as well as other related examinations. Share it with your friends and don't forget to like our videos. I'll see you in my next video lesson.